When a drone flies beyond the horizon, traditional radio links die, forcing the aircraft to rely entirely on cellular networks and orbital satellite constellations to maintain its digital connection. This video explains the exact engineering infrastructure, networking protocols, and routing modes that allow an industrial UAV to safely operate across continents. To stream high-definition inspection video while sending real-time flight commands, an enterprise drone cannot simply use the same public mobile network as a standard smartphone. Standard consumer cellular traffic is highly volatile and susceptible to sudden bandwidth drops. To solve this, industrial BVLOS operations utilize a core feature of 5G infrastructure known as network slicing. By leveraging the URLLC framework, which stands for ultra-reliable low-latency communication, telecom operators can isolate a specific virtual slice of the network exclusively for autonomous aviation. This guarantees a dedicated bandwidth with an air interface latency of less than 1 to 5 milliseconds, completely independent of consumer cellular traffic on the same tower. However, the true challenge for a cellular drone is the cell handover process. As the aircraft moves through space at 70 kilometers per hour at an altitude of 100 meters, it constantly transitions from one base station or G-node B to another. During a standard smartphone handover, a brief packet loss goes unnoticed. But for a UAV running a tight telemetry loop, a hard handover drop can trigger an accidental failsafe. Advanced BVLOS flight systems use dual SIM or multimodem configurations executing soft handovers, where the drone establishes a firm connection with the next cell tower before breaking the link with the previous one, ensuring a seamless packet stream in the telemetry logs. When a drone flies over deserts, oceans, or deep wilderness, cellular coverage completely vanishes. The only fallback is SATCOM, satellite communications. But not all satellite orbits are created equal, and choosing between GEO and LEO constellations determines how you control your aircraft. Geostationary Earth orbit satellites, or GEO, sit at a massive altitude of nearly 36,000 kilometers above the equator. Because they match the Earth's rotation, they appear stationary in the sky, providing immense coverage zones. But the physics of distance cannot be cheated. The round-trip time for a radio signal traveling to a GEO satellite and back introduces a baseline latency of 600 to 800 milliseconds. This high latency completely rules out manual teleoperation. If an obstacle appears, your manual command will arrive almost a second too late. GEO satellite links are strictly reserved for emergency backup telemetry and steady, slow waypoint tracking via the L-band. For true real-time remote operations, we must drop down to low Earth orbit constellations, or LEO, such as Starlink or OneWeb. These satellites orbit at just 500 to 1,200 kilometers. This short distance shrinks the latency budget down to an impressive 30 to 50 milliseconds, matching or even beating terrestrial fiber connections. The engineering bottleneck on the drone shifted from software to hardware, power, and weight. LEO terminal requires a phased array antenna capable of electronically steering its beam to track satellites moving across the sky at 27,000 kilometers per hour. In modern BVLOS engineering, these terminals are miniaturized into flat, airborne panels integrated directly into the UAV's upper fuselage, drawing high current directly from the main power distribution board. How does a MAV-link telemetry packet safely travel from a drone flying over a remote facility, through the public internet, and onto an operator's monitor on the other side of the planet? It requires a highly secure, low-overhead networking stack optimized for real-time performance. Traditional VPN protocols like OpenVPN are too heavy for BVLOS flight controllers. Their encryption overhead increases packet size, creating latency spikes and jitter. Modern UAV communication systems utilize WireGuard tunneling. WireGuard operates directly in the network kernel space, providing state-of-the-art cryptography with minimal computational impact on the drone's companion computer. The communication stack is strictly divided. The primary telemetry channel uses UDP, User Datagram Protocol, to transmit real-time state vectors like attitude, airspeed, and GPS coordinates. Because UDP does not wait for packet acknowledgements, a single dropped frame due to a temporary cell towers glitch is simply ignored, allowing the next fresh packet to arrive instantly without stalling the stream. Conversely, critical mission commands, such as uploading new waypoints or altering a geofence, are routed through TCP Transmission Control Protocol. TCP guarantees that every single byte is accurately received and acknowledged. If a packet is lost, TCP forces a retransmission, ensuring that the autopilot never executes a corrupt or incomplete mission command. Every industrial BVLOS flight system operates under one of three distinct control modes, balanced between network performance and local autonomy. Mode number 1. Direct teleoperation. This is manual flight over IP. The remote pilot uses a joystick connected to a ground control station that transmits control inputs via UDP directly to the drone, while a high-efficiency video codec like H.265 streams real-time footage back. This mode requires an optimal 5G URLLC connection with an end-to-end latency budget below 100 milliseconds. It is highly interactive but demands maximum network stability. Mode number 2, Cloud-Routed Waypoint Autonomy. This is the primary operational mode for large-scale commercial inspection. The operator does not manually steer the drone. Instead, a pre-computed flight path is uploaded to the cloud server and synced to the drone over TCP. The drone executes the mission locally using its internal navigation algorithms. Telemetry is streamed back to the cloud for monitoring, but even if the cellular connection drops completely for 5 minutes, the drone continues its task blindly and safely, completely unfazed by network dropouts. Mode number 3, Dynamic Hybrid Fallback. This is the pinnacle of mission resilience. The drone's companion computer continuously monitors the SINR signal-to-interference plus noise ratio of the 5G modem alongside the link quality of the SATCOM terminal. As long as the 5G link stays healthy, all heavy data and video stream through cellular towers. The millisecond the 5G SINR drops below a critical threshold due to terrain shading, the companion computer instantly reroutes the primary MAV-link telemetry stream to the LEO satellite link, while dropping the heavy video feed to preserve bandwidth. The handover is completely invisible to the autopilot, ensuring uninterrupted operational command. When a BVLOS drone suffers a catastrophic connection loss, the post-crash investigation focuses entirely on network packet forensics. An experienced UAV support engineer will immediately open the flight logs and cross-reference the heartbeat messages of the MAV-link protocol. If the logs reveal that the heartbeat signal from the ground control station vanished, but the local drone internal telemetry loop was still recording data onto the SD card, the hardware is proven innocent. The root cause is a network timeout event. Modern autonomies handle this via strict tiered failsafes. If the connection is lost for more than 5 seconds, the drone stops in midair and enters a hold pattern, waiting for the VPN tunnel to reestablish. If the timeout exceeds 30 seconds, the EKF activates the Lost Link Return to Home protocol, executing a pre-programmed autonomous flight plan back to the launch base, using local dead reckoning and internal obstacle avoidance sensors to survive without a single byte of external connection. BVLOS engineering is where telecommunications physics intersect with aerospace automation. By understanding network slicing, latency budgets, and secure protocol encapsulation, we build autonomous infrastructure capable of conquering industrial missions safely and globally. Subscribe to BlackBox UAV for more technical deep dives into flight data forensics, drone networking, and autonomous system architecture. Drop your technical questions about 5G routing or SATCOM latency in the comments below. This is BlackBox UAV. Analyze your networks, optimize your packets, and fly safe.